Hello folks, my name is Tim and welcome back to my channel. So today we're going to be looking at some stepper motors and we're going to be using the Raspberry Pi Pico to control them via a PIO routine. So that should be pretty interesting. Specifically, we're going to be looking at this little stepper motor here. So this is a 28BYJ48 stepper motor. It runs on 5 volts. And it's just about the smallest and cheapest stepper motor you can buy. And for that reason, it's very popular. Now, these little steppers are usually paired with one of these driver boards. So this is a ULN 2003 driver to power this little stepper. And it's very, very easy to use. You can get these things usually in Arduino kits and things like that. You know, those big project bundle packs that you can buy with loads of sensors and things in. They usually have one of these motors and one of these drivers. So to use it, very, very simple. You just plug your stepper motor in like so. And you need to power this thing. As I said, it's a 5-volt stepper motor. Apparently this board will also accept 12 volts, but I think 5 is plenty given the motor's rated at that. So we'll put a supply. Let's make sure I get the polarity the right way around. There we go. So those are our power supply pins. There we go. And then we need 4 inputs for controlling it, for sending the control signals. So I've got 4 cables here, and we'll just put those onto this little header there. There we go. And then these guys will connect on the other end into our Raspberry Pi Pico. So here we go. We're just going to put them into our breadboard, if I can get them in the right order. Right, there we are. So I've just set those up so that they align with GPIO pins 2, 3, 4, and 5. So that's how we're going to control it. There's really nothing to wiring up one of these things. As you can see, it's very straightforward. So we'll put some power into this guy. I've just got my benchtop supply set up here to deliver 5 volts. There we go. All right, so now that we've wired this thing up, how do we actually make it move? Well, that's relatively straightforward, actually. This is a stepper motor, and as with all stepper motors, it works by dividing the 360-degree rotation up into a number of discrete slices called a step. So in the case of this motor, it divides that 360 degrees up into 64 discrete steps. It also has a gearbox in here, though. There's some gears in here which have a 1:64 gear reduction. So taking that 64 steps per rotation into account and calculating for the gears, it actually gives us 4,096 discrete steps per rotation. So that is a lot of individual positions that this motor can effectively be set to. And that's using full stepping. You can actually make stepper motors do something called micro stepping, where you can subdivide the individual steps up into fractions of a step. And that can go all the way down to 32 times micro stepping, meaning instead of doing a single step, you do 1/32 of a step. And you can imagine then you can get some very, very precise positioning out of stepper motors. There are pros and cons for doing micro stepping, but on a little motor like this, especially one that's already running through a gearbox, we won't bother. We'll just do full stepping for this, and that should be absolutely fine. So how do we actually make the thing advance by a step? Well, that's where the controller chip comes in. So within this motor, there are a number of magnetic coils arranged such that the coils are next to each other all the way around the circumference. They are wired up in such a way that they're grouped into 4 discrete magnetic phases. And each phase can be turned on or off by triggering one of these control pins. So when you want to turn the motor, what you'd first do is you enable the first magnetic phase, then you will disable that magnetic phase and enable an adjacent phase, which should energize an adjacent coil within the motor and cause the shaft to turn by one step. So what you do is you enable the first pin, then you disable it and enable the second pin, then you disable that pin and enable the third pin, and so on. Once you've enabled the fourth pin, you then swing back around to the first pin again. Very, very simple. There's actually 4 little LEDs on the control board here which illuminate when each of the phases are enabled. So that's quite useful for debugging this thing. You can actually see visually what's going on as those phases cycle around. So I've already written a little bit of software that's running on the Raspberry Pi Pico to do that. So let's give it a whirl and see what it looks like. All right, and there we go. So we can see the phases being activated in sequence as shown by the LEDs, and the stepper motor is actually turning. It might not be too clear because I'm running this very slowly. The frequency at which you activate these phases is significant to how well the motor will perform. Running it at such a slow speed, the motor isn't going to do very well. But I'm doing this so that you can see a nice illustration of what I was talking about for activating these things. So what I'm going to do now is I'll turn the frequency right up, and we'll see the motor turn around nice and comfortably, but these LEDs will be flickering so fast that they'll basically look like they're permanently switched on. And that's a little bit more like it. So there we are, the motor is now running at a very happy, comfortable frequency. Obviously the LEDs aren't really helpful at this point, but we can see the motor's moving and everything's working the way it should do. So, all right, that's enough of that. Let's take a look at the software that we're actually using to control this and how you can do it with the Raspberry Pi Pico and MicroPython. Okay, so here we are at my Raspberry Pi 400 desktop, and I've loaded up the source code for the control program that we were running on the Pico. So it's a very basic, simple bit of software. But it does demonstrate one really nice feature of the Raspberry Pi Pico, and that is its ability to do PIO, or programmable I/O. What that actually means is you can create a I/O routine using a very simple instruction set that runs on a dedicated hardware within the Raspberry Pi's chip, and it runs independently of the main CPU. And that's really useful because if you have a very tight loop that you need to run, maybe you're generating a PWM signal or you're using some sort of real-time communications protocol or something, then rather than tying up your CPU running that all the time, you can offload it to a PIO routine and let it get on with it. And then the CPU is free to do more interesting things. So this is a really lovely feature. So what I've set out to do here is to build a PIO control routine for driving this stepper motor. So this was the first attempt. So let's take a look at what we're actually doing. So to make a PIO routine, the first thing you need to do is to create something called a state machine. And that's how you do it. This command here builds a state machine to run the program just called prog. It runs it at a particular frequency that you can specify here. And this final parameter, this set base equals pin 2, that instructs the state machine to use an offset into the GPIO pins that begins at pin 2. So when I say set the first pin high, that's understood to mean set GPIO pin 2 high. And you can set adjacent GPIO pins high from within the routine. You can use all the pins, but you have this kind of offset into them. So once you've created your state machine, you can activate it by setting active flag true. And because we're not running on the CPU, we've actually got nothing to do at this point. So all we do is go to sleep. So here we just sleep the CPU for a little bit whilst the PIO routine runs and does its job. Then later on, once we wake back up again, we deactivate the routine. And this command here, this just cleans things up by setting all of the pins back to 0. So there you are, very little to it. So let's take a look at the routine itself. We'll start here. And this set pins and then 8 is actually using a binary value to set a number of GPIO pins to either high or low. And that's controlled by a bit in the binary value that you provide. So here, this 8 is actually a binary value 0001. So that's going to set the first GPIO pin, which is pin 2. You remember we set the set base here. So pin 2 is going to be set low, pin 3 low, pin 4 low, and pin 5 will be set high. This final little bit here means delay. So each of these instructions features the optional choice of adding a delay for a number of cycles before the next instruction is executed. I've put a lot of delays in here, and this was to deliberately slow down the program for the purposes of demonstrating it. Otherwise, it just runs too fast and you can't really tell what's going on. So we set the first pin high, which is pin number 4, GPIO pin 5, but we can ignore the actual GPIO pin specifics now and think of it as the 4th pin. That'll be set high. These no-ops don't really do anything at all. They are literally just here to slow the program down. Then we have another set pins command here, and this is a different binary value. This is 0010. So that sets pin 4 that was previously high low, sets pin 3 high, and leaves pins 1 and 2 low. And then we have 2 and then we have 1, and those are the binary values that you would expect, so that we energize the 4th phase, then the 3rd phase, then the 2nd phase, then the 1st phase, and we loop around again. So when a PIO routine like this finishes, runs out of instructions, by default, it will jump back to the top of the procedure and it will start all over again. So this will just keep on cycling the phases 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, 2, 1, round and round and round and round, and that causes our motor to move. And that's really all there is to it. It's very, very simple, with the added benefit that we're not using up our CPU. I really love this PIO stuff. So once that was working and we'd actually got it to do something interesting, it was time to make the program a little bit more advanced. So the second stab at this program, and I'll be uploading all of this source code to my GitHub page, so if anybody is interested in taking this stuff, building upon it, or just using it as an example, I'll put a link in the description where you can go and get it. Anyway, so the second, more advanced version of this program, slightly different, but effectively it's doing the same thing. And what this does, it uses the pull command. That is how you communicate between a running state machine and the CPU. There is a mechanism, a transmission FIFO, that's a first in, first out queue that you can push values onto from the CPU side and pull those values off of in the PIO routine. And that's exactly what we're doing here. We are pulling a value from the FIFO, and we are then using a move instruction to move that value. So the OSR here, that stands for the output shift register. That is where the value ends up when you use pull. And we're going to take that value and use a move command to move it into the Y scratch register. So you don't really get a lot of instructions and you don't really get a lot of flexibility in these PIO routines, so you have to be a little bit clever in how you design stuff. You actually only get 2 scratch registers, one called X and one called Y. So those are effectively variables, you can think of them that way. So you really only get 2 variables to play with and a few other specialized registers for doing different things. It's not a lot, but it's enough. So once we've taken the value from OSR and we've put it into Y, we do exactly the same thing here, only in this case we're putting it into the X temporary scratch registry. And let's have a look here on the CPU side. You can see these are the values that we're pushing in. So the first thing we put in is this weird looking number, but it's actually a binary mask for controlling the 4 individual phases of the motor. You can see there how it breaks out into these individual nibbles. That's 4 bits. We're actually going to put that in twice because this is a 32-bit value and we only need 16 bits to express our pattern. So we'll just fill up the rest by putting the pattern in twice because we're going to loop through this thing anyway, so it doesn't hurt. The second value here, sm.put1000, that instructs the program how many steps it should run. Normally when you control a stepper motor, you don't turn the motor on and let it run, then turn it off. You normally instruct it to run for a specific number of steps. That is to say, turn to a very specific and precise position and stay there. So for this control program, you can do that by setting the number of steps that the motor should turn using this second push. So that comes out in X within the procedure. Immediately then we have this jump command here. This is an if. This is how you do conditionals inside of these PIO programs. And this is saying not X. What that means is the jump will jump to a named label if the condition that it's been told to check for is true. So not X means jump if X is 0. So if the user of this routine said move the stepper motor by 0 steps, we need to check for that explicitly and jump to the end of the program. Otherwise we'd accidentally move at least 1 step, which is not what the user wanted. Right, so the next thing we come down to here is this loop. So we declare a label for the top of the loop here, and then we have immediately this additional jump statement on this strange looking thing called not OSRE. What on earth is that? Well, the output shift register allows us to put a value into it and then to shift bits out of it. That is to say, if we have a 32-bit value in there, we can shift up to 32 bits of data out of that register bit at a time, or a number of bits at a time, which is quite useful. But you can only hold so much in the OSR. So this check here simply says, is the OSR empty? If it is not empty, it jumps over this next instruction here. If it is empty, this move instruction simply puts the value of Y back into the OSR. So if we deplete the OSR, we refill it with the original value so that we can keep looping around and around and around. So within the main body here, we have this little bit of code, and this should look a little bit familiar to the previous program. Rather than the set command, we use out. So out takes a number of bits from the OSR and puts them somewhere else. In this case, we're putting them into the pins here, and we're using 4 bits. So this is going to take the next 4 bits from the OSR and write them out to the pins. That will effectively set the GPIO pins high and low based on the pattern that we have provided. So it's exactly the same as in this program, although rather than explicitly saying set it, set it, set it, set it, we're just reading the values out of the OSR 4 bits at a time and doing the same thing inside of a loop. Now the loop is going to run for X cycles stored in the X scratch registry there. To do that, we use this final little jump here that says jump XDEC. What that means is test the X value, and if it is not 0, jump to the label. At the same time, decrement the value of x. So if x is 5 when we come here, it will go, yep, okay, that's not 0, so I will jump back up to the top of the loop, but I will make x now have the value 4, and so on. So eventually you loop around until you've completed the number of iterations you've been asked to do, in this case, the number of steps that the motor needs to move by, and the program can end. So here I've just got a little final command that just sets a pin high, and that's just to tell me that the program main loop has finished and everything's fine. So there we are. That's a slightly more complicated version of the first program, but the goal is to allow us to specify the exact number of steps that we would like the stepper motor to move by, with the added advantage that we can control the movement pattern if we wanted to enable any micro stepping or anything like that at a future date. Pretty good, but we're not quite done yet. So the final version of this program, and I will put all versions up because the simpler ones are nice as an illustration for people learning this stuff, but the final version, the completed version of this program, looks like this. So the main body of the PIO routine is essentially the same. We're doing that loop, we're doing the OSR bit shifting stuff, and we reload the OSR with the movement pattern should it become exhausted. But at the end of the program, we now have this little thing. What's that? Well, that's an IRQ. So we already know how to push data into PIO procedure, but how do we communicate back to let the CPU know we've finished with what it wanted us to do? Well, you use an interrupt. There we are, raise your interrupt, and in MicroPython, that's implemented like this. You just set the IRQ to a Python method, and then when the IRQ is raised in the PIO routine, the method is called, and that's on the CPU side. So we can be, in fact, asleep. You see, we're just sleeping here, but we'll still get the IRQ called and we'll still execute this routine even though we're sleeping. So there we are. That's nice and simple. There's a bunch of interesting bit shifting and stuff going on here, and that's because when you move the stepper motor by a number of steps, what you want to do when you send another instruction to move the stepper motor again by some more steps, you want to resume the movement pattern where you left off. So if you move the stepper motor, let's say 5 steps, you will basically go through a movement pattern 1, movement pattern 2, movement pattern 3, movement pattern 4, then you'll loop back to movement pattern 1. So the next time you ask the stepper to move, it should begin moving at movement pattern 2. Then go to 3, then go to 4, then go to 1. So all we're doing here is we're adjusting the stepper movement pattern that we want based on where we got to last time. There are 4 discrete phases. We have 4 possible permutations, just to say starting at 1, we're starting at 2, we're starting 3, or we're starting at 4, and that's just stored in this little list here. So whenever the IRQ is called, I simply update the bit mask by shifting these values down and packing them into a 32-bit integer, and then using put to pass that into the PIO routine along with the number of steps we'd like the motor to move by. So here we are just moving the motor 500 steps. Then once that finishes, we have a little sleep. Then we move the motor by another 500 steps. We have a little sleep, and so on and so on and so on until our 50-second sleep down here expires and the program exits. So there we are. That is the basis of a pretty reasonable stepper motor control routine. The only thing it's missing is ramping. Now, ramping refers to the ability to speed up or slow down your stepper motor at the beginning or end of a movement. That means if you've got a large mass connected to the motor and you try to move it instantly at full speed, or you try to come to a dead stop, you will probably find it won't work, and that's because the torque of the stepper motor is not sufficient to defeat the inertia of the mass that you're moving. And the net result of that is usually lost steps. And as anyone who's seen those lovely photographs of 3D printers producing plastic spaghetti instead of a nicely formed part knows, lost steps are a bad thing. Anyway, ramping is a task for another time. I'm going to upload all of this code, so anybody who fancies hacking on it or using it as a starting point for their own projects is very welcome. But that's plenty for now, so I hope this has been useful, and thanks for watching.